Hello, welcome back. This is our 12th lecture, and we're going to be going over chapters 3.1 and 3.2, quadratic functions and application, and then introduction to polynomial functions. All right, here we go. First, a quadratic function. A function defined by f of x equals x squared plus bx plus c, where a is not 0, is called a quadratic function. For example, if you had f of x equals 2x squared minus 3x plus 7. So this would be a quadratic function. It's important that a is not 0 because if we eliminate our first term, what we would have left over would just be a linear function. So this is a quadratic function because it has the x squared. By completing the square, the vertex form is expressed as f of x equals a times x minus h quantity squared plus k. The graph of f is a parabola with vertex h comma k. And if a is bigger than 0, the parabola opens upward and the vertex is the minimum point. However, if a is less than 0, the parabola opens downward and the vertex is the maximum point. The axis of symmetry is always x equals h, and it would be here. Okay. Example, we have f of x equals -2 times x minus 1 squared plus 8. So we can kind of use our function transformations from the last lecture to try and graph this, because we know that the parent function of a parabola looks like this. However, we are shifted 8 units up and 1 to the right. So that means we'll have something like this. So here's our vertex. Our vertex is going to be the point 1, 8, since this is going to be our h and this is going to be our k. And remember, in the standard formula of the vertex form, it's x minus h squared plus k. All right, and then we have this -2 here. So the negative tells me my parabola opens downward. So this is my vertex. A is -2, which means it opens down. All right. So we're going to have something like this. And then remember, since it is -2, the 2 stretches the graph vertically. So that was also covered in our transformations. And don't forget, there's that table on those last lecture notes where you can see all of the function transformations. All right, so here's my parabola. Let's keep going. So now the goal is to write this problem in vertex form. So recall that vertex form is f of x equals a times x minus h quantity squared plus k. So what we're going to do is a process that's called completing the square. And completing the square comes from when you square out a binomial, you get a squared plus 2ab plus b squared, okay? So essentially what we're going to do is we're going to say, okay, we have f of x equals x squared plus 12x, and then we're missing 5, square root of 5 is an irrational number. So we don't want that. We want some sort of squared term, like this b squared, to be at the end. So we want to do plus something, and then we also subtract it. That way we're not changing the problem. So the strategy in finding this b squared right here is we're going to take our middle term, which is 12x, and we're going to take the 12, and you're going to do 12 divided by 2 squared. So 12 divided by 2 is 6, and 6 squared is 36. So we want to add 36 and at the same time subtract 36, because that means we're just adding 0 to our problem, since 36 minus 36 is 0. It's very important to always remember to subtract the number that you get from your completing the square, so that way you're not changing the problem. So now I have a perfect square. It's right here. X squared plus 12x plus 36. So what you can do is you can realize all you did was find this last b squared term to be able to take this trinomial and revert it back into a binomial, or you can also try to factor it. So if you did factor it, you would get 36, which is 6 times 6 is 12. So that means you'd have x plus 6 times x plus 6, which equals x plus 6 squared. Either way, you can see how we have x plus 6, 12, and then we have this trinomial, which is the same as this guy up here. We have something plus something squared equals. So this is our something plus something squared. So this is going to equal x plus 6 quantity squared, and then we just have that minus 36 plus 5 tacked on to the end. So it's going to mean f of x equals x plus 6 quantity squared minus 31. And that's it. And now you can tell that your vertex is -6, -31. The vertex is -6 because remember the equation for vertex form is x minus h. And since we have a plus inside of this parentheses, you'd think of that as x minus -6 squared. So that's why we get -6 instead of positive. All right, let's keep moving on. So completing a square is a long and taxing process, but we would like a fast way to find the vertex when we're given an equation in standard form. And we can do that by taking the negative b over 2a as our x value, or our h really, because we have and then this would be our y value, just plugging that back in. So looking at our standard form of an equation up here, we can see that our a would be -1, since we have -1x squared. Our b is going to be 4, and our c is -5. Okay, so that means our vertex h comma k will have h equals -b over 2a, which is going to be -4 over 2 times -1, which is -4 over -2, which is 2. Okay? And then our k is going to be f of 2, which is going to be -2 squared plus 4 times 2 minus 5, which is -4 plus 8 minus 5, which is going to be -1. So that means our vertex is going to be 2, -1. All right, let's keep going. A stone is thrown from a 100-meter cliff at an initial speed of 20 meters per second at an angle of 30 degrees from the horizontal. The height of the stone can be modeled by h of t is equal to -4.9 t squared plus 10t plus 100, where h of t is the height in meters and t is the time in seconds after the stone is released. Determine the time at which the stone will be at its maximum height. So we know that this is going to be a maximum because we have this negative out front that tells us we're going to have an upside down parabola. So our max is going to be the vertex, h comma k. And remember, the time is going to be the x value, and the height is going to be the y value. All right, so we essentially just want the h coordinate because that's going to be the time at the maximum height. And remember that h is equal to -b over 2a. So in our equation here, we're going to have a is equal to -4.9, b is equal to 10, and c is equal to 100. So that means our x coordinate of our vertex, which we call h, is going to be -10 divided by 2 times -4.9, which is equal to negative 10 divided by 9.8, which is going to be 1.0204. All right, moving on. So this is the same example, just continued. Determine the maximum height and then the time at which the stone will hit the ground. Well, remember, the maximum height is going to be the k coordinate of my vertex. So all that I really need to do is plug in 1.0204 into my function here. So that means I'll have, so let me copy down the function. So I have h of t equal to negative 4.9 t squared plus 10t plus 100. And we want to plug in when t is equal to 1.0204. So we'll have h of 1.0204 is equal to 105.20404. So this is going to be our maximum height. So if we're trying to find the time at which the stone hit the ground, you want to think about if you actually throw a stone or any object, when it does hit the ground, it has a height of 0. And also think y equals 0. If something is on the ground, it has no height, right? So that means we want to set our function h of t equal to 0. And our function h of t is this negative 4.9 t squared plus 10t plus 100. And how we're going to figure this out is we're actually going to use the quadratic formula. If you don't remember the quadratic formula, I'll write it for you over here. It's going to be x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. This is the quadratic formula. And we use it whenever an equation that we have is just too difficult to try to factor or complete the square. And with this negative 4.9 as our a, this would be very, very difficult to factor or complete the square. So we are going to use our quadratic formula instead. So now we'll have a is equal to negative 4.9, b is equal to 10, and c is equal to 100. And I'll box this guy in. All right, so now we're going to have x equals negative 10 plus or minus the square root of 10 squared minus 4 times negative 4.9 times 100 divided by 2 times negative 4.9. So I don't recommend putting all of this into your calculator at one time because it can be rather difficult. I like to kind of solve what is under the square root first. So I'll go ahead and do that off to the side. So 10 squared minus 4 times negative 4.9 times 100 is going to be 100 plus, because we have this negative times a negative, 19.6 times 100, which is going to be 100 plus 1960, which is equal to 2060. And now this is what goes under the square root. I'll have x equals negative 10 plus or minus the square root of 2060 divided by, and then 2 times negative 4.9 is negative 9.8. All right, this is much better to put in the calculator. So the first thing we'll do is x equals negative 10 plus the square root of 2060 divided by negative 9.8. That's going to be approximately negative 3.61. And that's not good because we can't have a negative height, right? That would imply that the ball is like plummeted down into the earth. So that doesn't make sense. So we reject this solution. And then we try the other one, which is going to be negative 10 minus 2060, square root of 2060 divided by negative 9.8. I'm going to erase this scratch work and write that over here in this area. So we'll have negative 10 minus the square root of 2060 divided by negative 9.8 is going to be approximately 5.65, which is your final solution. So this is the time, so t equals 5.65 at the point the stone touches the ground. That means from the moment that you threw the stone to the moment it touched the ground, 5.65 seconds have elapsed. Just to clarify one more thing, the reason I separated it into a plus and into a minus is because our quadratic formula has plus or minus. So you need to do those two individually, where you first add the square root and then divide by negative 9.8. Then the second is you subtract the square root and then divide by negative 9.8. All right? All right, let's keep going. Okay, so now we're going to move on to polynomial functions. And with polynomial functions, we will have end behavior that we will want to consider. So essentially, end behavior is what your function is doing towards infinity. And as x goes to negative infinity. So we are curious as to what happens to functions as x goes to infinity and as x goes to negative infinity. So if we have this polynomial function here, and I know it looks like a crazy amount of numbers, but all this is really just saying is we have a term for each exponent. So we could have like f of x equals 2x to the fourth minus 3x to the third plus x squared minus 1, for example. So then our n here would be 4. So that's all polynomial really means is many numbers, right? Poly is many, so polynomial, many numbers. So as x goes to infinity or as x goes to negative infinity, f eventually becomes forever increasing or forever decreasing and will follow the general behavior of y equals just the first term. That's a lot of words, right? All this is saying is if we pick on our function here, that means our end behavior will follow f of x equals 2x to the fourth. So whatever 2x to the fourth does, our long function is likely going to do as well. All right, and then we have some cases here. So if n is even, this means if your exponent is even, you'll either have both tending upward or both tending downward, depending on whether or not your leading coefficient is positive or negative. It was the same way with parabolas, remember? When we had a positive leading coefficient, our parabola opened upward, and a negative one, our parabola opened downward. So you can kind of compare it to what we were just doing. And next is if n is odd, that just means if your exponent is odd, we're going to have from the left, so this is from negative infinity, will be tending downward, and as we go to positive infinity, we'll be tending upward. You can remember this or compare it to either y equals x, which looks like this, right? Or y equals x cubed, which was this function here, right? If on a plane. And then here, if your leading coefficient is negative, then your roles are reversed. So as x goes to negative infinity, your y is going to positive infinity. And as x goes to positive infinity, your y goes to negative infinity. Let's go ahead and go through some examples on determining end behavior, and hopefully that table will make more sense. So we're going to use the leading term to determine the end behavior of the graph of the function. So for the first one, my leading exponent, or my largest exponent, is 5, which is odd. So that means I'm either going to choose from this one here or this one here. Next, I look at my coefficient. My coefficient is a -4. So that means as x goes to negative infinity, y goes to infinity. They're flipped. You see negative, positive. And as x goes to positive infinity, y is going to go to negative infinity. So I am going to have something like this, right? Same as this guy here. Not an exact drawing, but this is the gist. Okay, let's do number 2, because number 2 is going to be a little more complicated. So for number 2, I'm actually going to sum up all of the exponents. You can't forget about this little guy up here. You can think of him as x to the 1. And then here's a 3, and then here's a 2. So that means I have 1 plus 3 plus 2, which is going to equal 6. So that means my highest exponent is going to be 6. Now you could take the time to multiply all of this out, but that's going to take you a very long time. However, if you did multiply all of it out, you would have your first term as some coefficient times x to the 6th, right? Okay. And then I'm going to look at the coefficients in front of my x's. So this one just has a +1, this one has a +2, and this one has a +1/4. So that means my leading coefficient is going to be a positive number. And when I have an even exponent and a positive number leading coefficient, where you could have done like the a bigger than 0 thing, we know that I'm going to tend upward both ways, right? According to this chart. So when you have a positive leading coefficient and an even exponent, both arrows are going to go upward according to my chart. So that means as x goes to negative infinity, y is going to go to infinity. And as x goes to infinity, y is also going to go to infinity. So this is the going upwards forever. Okay? Let's move on. Determining the zeros. So we want to find the zeros of f of x equals x cubed plus x squared minus 9x minus 9. If you don't remember, we are going to use the factoring by grouping for these problems. So when you factor by grouping, you essentially group together two terms that have something in common first. So I'm going to pick x cubed and x squared and then negative 9x minus 9, because these both have a GCF of x squared, and these two have a GCF of negative 9. All right, so now I'll have x squared times x plus 1. Since if you redistributed this x squared, you'd get back x cubed plus x squared. Next, I'll have minus 9 times x, and then this is the tricky part, plus 1, because negative 9 times positive 1 gives you negative 9, which is what we desire. All right, now this is kind of weird. You want to think about the GCF again. If you think about x plus 1 as just a number, we can factor out an x plus 1. Kind of similar to if you have 2x plus 2 and you say that's just 2 times x plus 1. Well, I have x squared times this minus 9 times the same thing. So I can pull him out front, and then everything left over goes in the parentheses, right? Okay. So now to find the zeros. Well, zeros of a function just mean that 0 equals x squared plus 1, x plus 1 times x squared minus 9, which means that either 0 equals x plus 1 or 0 equals x squared minus 9, and then you can solve both of these individually. So this is -1 is equal to x, and this is going to be 9 equals x squared, which then we take the square root, and we get plus or minus 3 equals x. So my zeros are going to be -3, -1, and 3. On a graph, what that would look like, so we have 1, 2, 3, 1, 2, 3. So I'd have a 0 here, a 0 here, and a 0 here. And we could actually graph this if we wanted to. I'm going to go ahead and graph it just to show you that it can be done. So we look at our leading term. Our leading term is x cubed. So that makes this an odd exponent. And it has 1 as a coefficient. So it has, you could think a equals 0, or you could think of a positive leading coefficient. And if we come back up to our chart here, exponent is odd, and positive leading coefficient means we start down and we end up. All right? So looking here at my graph, I'm going to start down here according to my chart, and then I cross here, cross again at my other 0, and then cross at my third one and end up. And that's how you graph a very large polynomial function without plugging in every single number that you can think of. It's a little trick. Okay, let's keep going. In general, multiplicities are essentially what makes a 0 of a function cross or bounce on the graph, or on the x-axis, really. So the multiplicities are either odd or even. So if we have some function f, and we have a real 0 that we call c, then the point c comma 0 is an x-intercept of the graph f. All that's saying is when we do this process that we just did, these points get graphed as x-intercepts, which we just did, so you can see that, right? Then if a 0 is an odd multiplicity, it crosses the x-axis, exactly how it did here. We crossed through this, we crossed through this, and we crossed through this because our multiplicities were all 1, right? This is x to the 1, and even though this one's x squared, we would still have x minus 3, x plus 3 as our zeros, right? These are all multiplicity of 1. If it has even multiplicity, then the graph, this book likes to use the word touches. I actually like to use bounces, but it is the same thing. The x-axis and turns back around. It does not cross the x-axis. An example of that would be y equals x squared. The only solution for this would be x equals 0, and it would have multiplicity of 2 because it comes from x squared. So that means my parabola, and hopefully you remember the parent parabola, my parabola looks like this. So you notice here at this 0, right, this is x equals 0, you can see it bounces or touches the x and comes back. So whenever things have an even multiplicity, they bounce, and when things have an odd multiplicity, they cross. Similarly with y equals x cubed. My x would be 0, and it would have a multiplicity equal to 3, because x cubed. However, my graph of x cubed looks like this, and here is x equals 0. So now you can see when they're even multiplicity, they bounce, and when they're odd, they're going to cross through. All right? Keep going. Now our goal is to graph this function. The very, very first thing you want to do when you're graphing a polynomial function is figure out the highest power of your exponent. And we're going to use the same strategy we did earlier. So step number 1, we're going to find our highest exponent power. So this is like x to the 1 here. This is also like x to the 1. And this has a squared out here. So it's going to be 1 plus 1 plus 2, which equals 4. So it has an even power, which means it's either going to be up and up, or it's going to be down and down. All right? Step number 2 is going to be to determine if your leading coefficient is positive or negative. So for that one, we can actually just observe the very front of this. We have a -2. Negative. Okay, so since it is a negative, that means we are going to go down and down, because only when the leading coefficient is positive do we get to go up and up. Remember parabolas, okay? Positive parabolas open up, negative parabolas open down. It's the same thing with polynomials. So even though it's exponent 4, because it's negative, it's still going to be completely downward, okay? Now step number 3 is going to be to find the zeros. All right, so finding the zeros, we are going to set each one of these equal to 0. So that means we'll have x minus 1 equals 0, x plus 2 equals 0, and then x minus 4 quantity squared equals 0. The first two are pretty straightforward, right? We'll just add 1 and we get x equals 1. We subtract 2, we get x equals -2. Both of these zeros have what kind of multiplicity? Well, let's think about it. What were their exponents? When it doesn't have an exponent, we assume that the exponent is 1. So these are both odd multiplicity, right? Their actual multiplicity is 1. All right, next, let's do the squared boy. So if we take the square root of both sides, the square root of 0 is just 0. Oops. And then we can add 4 to both sides, and we get x equals 4. However, this is now going to have a multiplicity of 2. Do you see why? Because of this squared term. There are technically 2 of these. We actually even could have split it up. We could have done, now I'm going to do scratch work over here to hopefully help y'all understand why it's still multiplicity 2. We could have done x minus 4 times x minus 4 equals 0, which then would have meant x minus 4 equals 0 or x minus 4 equals 0, and then we would have again gotten x equals 4, x equals 4. So you see, that's why the multiplicity is 2 and not 1, because there are 2 of these binomials. All right, I'm going to now erase my scratch work and graph this function. Graphing the function is technically the last step. You could think of it as step 4 would be to actually draw out your graph, okay? So first, on graphing, I'm going to put down my zeros. So I have x equals 1, x equals -2, and x equals 4. So here is -2, here's 1, and here's 4. All right. Next, I'm going to remember that from step 2, I'm going to be tending down and down on both sides. So that means I need to start from down here, and I also need to end down here, right? Then you look at the multiplicities. So since x equals -2 is odd, that means I'm going to cross here, okay? Cross through that 0. Next, x equals 1. that also is odd. It has multiplicity 1. So that means I'm going to also cross through that 0. Lastly, x equals 4 has a multiplicity 2, which is even. I'm going to draw that better. Cross. So since this is even multiplicity, this graph is going to bounce like so. Okay, and this was my attempt at drawing this polynomial function. I hope it made sense. So odd multiplicities cross and even ones bounce. And that is how you graph a polynomial function. So thanks y'all for tuning into this lecture. I hope y'all have a wonderful rest of your day.